Welcome to Math 108. Today we're going to talk about functions and function notation. So first of all, what is a function? A function is basically a relationship. Now, a lot of the relationships we're going to be looking at in this class are going to be numerical, right? We have numbers in, numbers out. But it doesn't have to be numerical. Your computer uses functions all the time. When you hit a key on your keyboard, your computer takes that keystroke and converts it to a binary code, which is stored on the computer. And that relationship between the keystroke and the binary code is a function. Or when you check out at the grocery store and you scan an item and the price comes up. The cash register has some sort of relationship stored in it between the barcodes that it scans and the price for that item. So functions are everywhere. And a function is, first of all, just a relationship, but it's a particular kind of relationship. It's a relationship that assigns exactly one output for each input. Okay, so like when you go to to the grocery store and check out, if you buy a loaf of bread, you know, if you say you buy 2 loaves of bread, you scan the same item with the same barcode, it's going to ring up at the same price. You're never going to get, hopefully, never going to have that case where you buy 2 loaves of bread and one rings up at, $2.99 and one rings up at $5.99. So you want to have one output for each input. Okay, so that's the distinguishing factor. That's what makes a function special. It's a relationship, but it's a special kind of relationship where there's exactly one output for every input. All right, now there's 4 main ways that we can describe a function. All right, with words, formulas, tables, or a graph. All right, so in this example here, we know that the area of a square is the square of its side length. So we can say that in words. We can also say that with a formula. So over here in this formula, instead of using words, I'm using the letter A. A represents area. And I'm using X to represent the side length. Side length. And this is just a mathematical sentence saying area is side length squared, right? That's just how you would read that formula. A equals x squared is the same thing as saying area equals or is side length squared, all right? Now we can also represent a function as a table. And sometimes that's all you've got. Sometimes you just have collected data on some relationship, and all you've got is the data. But in this case, if we're representing just the area of a square, all we've done is, okay, if the side length is 1, then the area is 1 square centimeter. If the side length is 2 centimeters, then the area is 4 square centimeters, and so on. Now you could just basically plug my numbers into the formula. But sometimes you don't have a formula. Sometimes all you have is data. Now we can take those numbers in a table and we can create ordered pairs from them and graph the data. So for example, in this first row of the table can become an ordered pair 1, 1, where x is equal to 1 and a is equal to 1, and then we can graph it. So here's x equals 1, a equals 1, and that's the point 1, 1, and we can just graph the points, right? Each one of these x and a values can become an ordered pair. So this would be 2, 4, and then we can graph that, and you can see here's that point right there, 2, 4, right, and so on. Now, because this is the area of a square, we know that the areas exist for side lengths that are other than these whole numbers, right? So, I mean, we could put in 2.235 and calculate the area for that as well, given the formula that we have. But we know that there's a continuous relationship, and so anyway, we can graph the data in the table. So we can represent a function as a graph as well. All right, so let's talk a little bit about the notation and vocabulary for functions. All right, So we say if we have a relationship between two things, or we have where there is a one output for every input, then we can say that y is a function of x, or um, y equals f of x. And we write that mathematically like this. We say that y equals f of x. This is basically saying the same thing here, that y is a function of x. It's just a mathematical way to write that statement. So now the x is the input to the function. Input. And you can think of the parentheses in this case as being sort of the receptor for the input. Okay, and then y is the output. Okay, so, and f is the name of the function. It's just the name. Okay, it's not a variable or anything like that. It's just the name of the function. We call that function f. It's the name of the function. And we're using the parentheses as being the receptor for the input. All right, now, so x is the input. It's also called the independent variable, right? Because that's what we can vary it independently, and then y is dependent on x. All right, so what x is often called the independent variable, y is the dependent variable. The input is also sometimes called the argument, and it's also an element of the domain. Y is the dependent variable. You could call it the value of the function, and it's an element of the range. Okay, we're going to talk about domain and range later, so we'll get into that more. We won't talk about that today. Now, these letters are fairly arbitrary. So right now I'm using x and y and f, right? So, but if we're representing, like in the previous sort of not really an example, but where I talked about the four main ways to describe a function, we were using a, right, for the output, right? So a was the dependent variable, and the side length x was the independent variable. So we don't have to use x and y, right? So if we have, for example, the relationship between the circumference of a circle, which is pi times diameter, maybe rather than using x and y, we want to use c and d, because that's more descriptive of what that variable represents. So rather than using x, we use d to represent diameter. Or instead of y, we can use c because it means something. It represents the circumference. And so sometimes using a letter that's more descriptive is helpful. So those letters are arbitrary. And the same thing with f, the name of the function. We could call it g, or we could call it g of x. Sometimes we have functions like ln of x or sine of x. All right, these are all just names of functions. Normally we just use one letter, but these are common functions that you'll run into in 109, where like this ln, that represents the natural log of a value, and it's just the name of the function. The input is x. This is the input to the function. All right, same way over here. This is the input. Right? Maybe you've heard of sine and cosine before, but this sine is just the name of the function, right? Just like we're replacing the f with sin. That's the name of the function. All right, let's go on to this first example. So, let's see. All right, so in this example, all we're asked is we're just using the function notation and understand how to what it means, right? So we're just going to use the function notation. So we have a table of values, and we're just asked what is f of 2. So we read this as f of 2. So this is the input, right? And the input to the function is x right here. So let me erase this little line. There we go. All right, so the input is x, and so this is saying what is the value of the function when x is equal to 2. So we can just look it up in the table. When x is equal to 2, y is equal to 4. Okay, so the value of the function at -2 Did I say 2? I meant negative 2 is 4. All right, let's look at B. This is asking for f of 0. All right, so this is our x value, and this is x. And so we want to look at, okay, here is our x value of 0, and what is the corresponding f of x value? It's a negative 2. All right. All right, so now C and D are a little bit different. So this is saying, okay, f of x is equal to 0. This is the value of the function is 0 for what value of x? All right, so now we're just going to use the table in reverse, right? We're going to look up the function value, right? This is saying f of x is 0. And so what is the corresponding x value? All right, it looks like it's 2. So, and there's no other zeros. Now with a function, you can have um, more than one x value that gives the same value of f of x. It's just that you can't, every x value has to have exactly one f of x value. Okay, so for example, this number 4, or this part D, we're asked what is x when the value of the function is 4. All right, now we've got several different 4s. We got a 4 here, not like that. I get a different mark highlighter. There we go. We have a 4 here. We have a 4 here. We have a 4 here. So here we have more than one value of x that gives the same value of the function. And that's fine. It's still a function. It's just, so just remember, it's just every input gives one output. All right. But you can have the same output value for different input values. All right. So it looks like this function is equal to 4 for x equals negative 2, 1, and 3. All right, that's all I have for you in this video. I'll meet you in the next video for the next example.